Okay, we can get started. So we'll just be trying a couple of problems throughout because it's a problem solving session. Maybe after every problem we can. We'll see how it goes. We'll see how it goes. So we have a triangle ABC. You'll also get to know my beautiful diagram drawing skills today. I'm excited for that. We have ADBECF as altitudes. And let X be any point. You want to show that circles AXD. Okay, so over here it's important to note that AX and D are not collinear. BXE. We are going to assume that's a circle, and CXF pass through another point Y. So they have to avoid something like this. Yes, much better. CF. We need to show that the third circle also passes through this. Fine, something like this. Is the question okay? Does the question make sense?
Yeah, the question is clear.
Okay. So if at any point you have an idea, we can discuss. And in the meanwhile, we just take some using GeoGebra, but that might be a little bit of cheating, I guess. Like in general, while solving problems, you should always don't use GeoGebra. That sometimes kills intuition a lot, but maybe just for the sake of this, let me try to get a better diagram. It's
Maybe
also fun
repeat
to work with bad
the triangles
diagrams.
again.
Yes, AXD. It's fun to work with AXD. I mean, everybody's on the same page and understanding the solution, it should be fine. So we have A and D are the right? So you want to consider that X and B and E and C and F with X. So we just have three circles and we want to show that this. I want to show that these three circles look something like this, right? So above that, isn't this the Mikkel's point? I don't think so. But anyways, we haven't discussed auditors yet, so you won't be going into that. So basically, so again, a big hint is since we're working with power of a point and radical axis and things like that, we know it's going to be something of that sort. So also it's not too hard to see. So what can you say about these three circles? We want to show they look something like this. So what are some observations that you can make in this figure, which are related to say power of point or radical? Guys, don't put it in the chat. Just say it. It's so much, it gives me happiness to hear your voices. Right. So somebody, as somebody mentioned, these three circles are coaxial, which means they have the same radical axis. So every pair of these circles have the same radical axis. Does that make sense?
Yeah.
Amazing. So now if we show that these three circles have the same radical axis, these three pairs of circles have the same radical axis, we'll be done. Right? So observation one, we need to show that these three circles have the same radical axis.
I think we can show that for every pair of circle, the radical axis passes through X and the orthocenter H.
Very interesting. So what is Harshit saying? Harshit is saying for every pair of circles, the radical axis has to pass through X because the circles themselves pass through, all of the circles themselves pass through X. And he's saying even the orthocenter, let's call it H, has to lie on the radical axis of all the three circles. Can somebody who's not Harshit explain why that has to do? So claim H lies on the radical axis of all three pairs of circles. So how could we go about proving this? Again, something lies on the radical axis.
This is just because HA times HT equals HB times HE equals HF times HC.
Amazing, exactly. So one way to show that something lies on the radical axis is to show that the power with respect to both the circles is the same. So, and like you mentioned, we know that HA times HD is the same as HB times HE. It's the same as HC times H, right? That's simply because, okay, that's also not too hard to see. If we have a beautiful triangle config sort of like this, then we know that this is 90 and this is 90. So we know that this is cyclic. So we know that HB times HE is the same as HC times HF, simply because of power of point of H with respect to this circle. And the same thing we can do everywhere. So we know HA times HD is HB times HE is HC times HF. And this finishes because HA times HD is the power of H with respect to AXT. So this is the same as power of H with respect to the first circle. Let's call it something. Let's call it omega 1. This one is, let's say, omega 2, omega 3. Omega is written like this. Omega 1, omega 3. Then we know that power of H with respect to all the three circles is the same. Shari Pranaventra?
Nothing. Sorry, I just joined the meeting a bit late.
Okay, no worries. Respect to all circles is the same. And hence it lies on the radical axis. Now we're done because we know X lies on the radical axis of all three circles We know H lies on the radical axis of all three circles. So we know XH has to be the radical axis. And it also tells us that the three circles have the same radical axis, which means they have to look something like this, which means that they intersect at exactly 2 different points. So we have shown that HX is the radical axis, and thus the three circles are coaxial. We are done. Okay, what are the main key things we used here? Basically that if we want to show that three circles concur, then we just need to look, and we already, let's say, know that they concur at one point. We just need to look for some other point which has the same power with respect to all the three circles. That was one key thing that we used here. Okay. Coaxial just means that they have the same radical axis. Okay. Now let's move on to this. Any other questions about any of this? So just one small thing I like to point out, that don't aim for solving the problem, but after you solve a problem, also try to look at the insights that you got from it. What were the things that we used? So when we see a similar problem, we can apply the same over there. Okay, I'm assuming there are no more questions. If there are, you can just put them in the chat or just unmute and ask. Oh my god, what is this? Yes, this is question number 2. We'll figure out the other mass later. In a quadrilateral ABCD, okay, so we're looking at something called as the complete quadrilateral configuration. So we have quadrilateral ABCD. For every pair of sides, or we look at pairs of points, pairs of vertices, and look at their intersections. So E is AB cap CD, F is AD cap BC, G is AC cap BD. Show that the circles with diameter AC, BD, and EF are coaxial. So this also seems fairly weird, but it's a very cool result. And I'll elaborate more on why once we're done with the proof. So you want to show AC, then one circle with diameter BD, and the circle with diameter EF are coaxial. Yes, this is the Gauss-Borden-Miller theorem. So since we've mentioned already, a very cool consequence, we have three circles which are coaxial. An immediate consequence is that since they have the same radical axis, their centers must also be collinear. So in fact, if we just apply this over here, we'll get to the proof of this in a while, but if we apply this here, we get a very cool fact that if we have any quadrilateral ABCD, then the centers of AC, BD, and EF are always collinear. Simply because they're the centers of these three coaxial circles. And that line passing through the centers is called the Newton-Gauss line. It's very cool. But yeah. Okay, so coming back to this question, you want to show that these three circles are coaxial. Again, it's very similar ideas to the other question. Well, let's wait for you guys to get something. So what are some strategies by which we can approach this question? How do we show that they're coaxial? So one way is to just look at the circles and look at the points at which they intersect. Or
Why
we
is
can try
D
to
there?
find.
Like, it's not even important, is it?
Yeah, true. I don't know why it's there. It's okay. Let it be. Okay, so what do we need to show? We need to show that they're coaxial. So now over here, in fact, we don't have here in the earlier question we knew that they were passing through one point on the three circles, and we wanted to show that the other point also they also pass through one other. All of them pass through one other point. Over here, we know that also. How could we go about showing their coaxial? Maybe strategy, by which we can approach this. So I think as somebody mentioned in the chat, look at, okay, try to find points which have the same power with respect to all three circles. Does this make sense? Can somebody explain why this would be a good idea? So if we find 2 points which have the same power with respect to three circles, then we know that the line joining them has to be the radical axis for all the three pairs of the circles. And then because that has to be the radical axis for every pair of circles. So the three circles are coaxial and then we're done. Also note that since we have diameters again, we also have a bunch of 90-degree points. Any ideas? Why don't we look at the orthocenters again? Try to see if we can get something else. And again, the motivation for looking at orthocenters is we have a bunch of 90 degrees because we're looking at diameters. Right? So what do we have? A, B, C, D. And let's say we want to look at the orthocenter. Okay, you guys tell me what orthocenter should we look at? So basically, we just want to look for points which have the same power with respect to all the three circles.
So we could look at the orthocenters of FAB and FDC and EAD and EBC.
Interesting. So if let's go step by step. What if we look at the orthocenter of FAB? So let's say somewhere over here. Let's call it H1.
Yeah, so like the orthocenter of so you could FAB and like it would be a radical center, I think.
Okay. Why would it be the radical center?
Uh,
The orthocenter of FAB has equal power with respect to all three circles. Okay, what is its power with respect to this guy? What is its power with respect to, let's say, the circle with diameter dB? This is fairly unintuitive. Let's look at this orthocenter of FDC instead. That might be easier to spot. Let's say that is somewhere over here. Call it H1. Now, what is the power of H1 with respect to, let's say, the circle with diameter BD? Or the circle with diameter AC? Hmm. Okay, let's drop the perpendiculars. Maybe that will make more sense. We know this is 90. We know this is 90. And we know this is 90. Okay, now somebody should be able to answer this. What will be the power of H? Okay, can somebody spot the circles here? We have three circles and we have this figure. So
Yeah, so but the perpendicular on FC would be the point which is on the circle with diameter BD.
let's call them X, Y, Z. So X, you're saying the point X is going to be on the circle with diameter BD. Do people see that? That's because angle DXP is 90 by definition because it's the orthocenter. So we know that H lies on the, DX is going to be a chord passing through H that lies on the the circle with diameter BD. So what is the power of H going to be with respect to circle with diameter BD?
HD into HX.
Exactly. So say it's going to be power of h with respect to circle with diameter BD is HD into h. Okay, now just quickly finish it off from here.
Similarly,
Yeah.
with
Mhm.
a circle with diameter AC, we have HZ is equals to HZ into HC, my bad.
Right. So Z is power of. So now notice that AZC is 90 simply because of the definition. And so power of H with respect to circle with diameter AC is going to be H, sorry, not, yeah, HZ into H.
And now if we look at the circle with diameter EF, it will be the power of H with respect to that circle will be FH into HY.
Exactly. Since FYE is 90, we know that power of H with respect to the circle with diameter EF is going to be HF into HY. So power of H with respect to circle with diameter EF will be HF into HY. And now what do we know? We know that since H is the orthocenter, we know that HF into HY is the same as HX into HY. It's the same as HZ into HC. We know that all these three quantities
This
are
is through
equal.
cyclic
So
quadrilateral property.
yes, that's because of this property that we consider. If H
Okay,
is the orthocenter, so we know that this will be the, if you consider
okay.
this circle, then we know the center this is the center this.
Yeah, got it.
Because so since it's the above
Your voice
three
is a bit
quantities.
lagging.
Oh, sorry about that. Is it better now? Can you hear me all right?
Yeah, it's clear now.
Yes. Center, the above three quantities are equal, and so we know, and thus H lies on the radical axis of all three circles. I hope this is clear so far. Now the thing is, what is stopping us from doing this for the orthocenter of, let's say, EBC? We can do the same thing for the orthocenter of EBC. It will be a very symmetric argument, and we'll get that that also lies on the radical axis of all the three circles. And there's also ways. So if you also do it for F, the orthocenter of FAB, I believe that also should work out. And so we get very powerful results because of this. So we get that those circles are coaxial. Their radical axis will actually the line passing through all the orthocenters that are formed. And we also get that the the three centers have to be collinear. And further, notice that the line joining the centers is always perpendicular to the radical axis. So we have that the line passing through the orthocenters is perpendicular to the line joining the midpoint. That's a
Can
lot
you
of cool
repeat the
things
argument?
to,
Can you repeat the
yeah.
argument for that FAB? I couldn't get it.
Okay, let's try to figure it out. I believe it. Okay, let's see.
Actually, your voice
FAB
is still
and
cutting a bit.
oh, I'm sorry. Let me just quickly take a look at what's wrong. hopefully. Hello? Am I?
You're not
You can't
audible, I
hear
think.
me.
No, your voice is cracking.
Okay. All right, now it should be better. Now there should be no issues. Is it fine now?
Yeah,
Yeah.
it's fine.
Okay, amazing. Yes. So
Actually,
now it's a
I've
very,
got a
very
question.
smooth
I
mode.
didn't get like, can
Okay.
you ask it now or later?
You can ask it right now.
Okay, so I don't see like why we taking like these triangles, why FDC and EBC like and FAD. Can we take like any triangle or what's the motivation for taking the triangles?
So we want to look at some orthocenter again because there's a lot of 90 degrees coming in. So it will be nice to look at some particular orthocenters. And very good when we have quadrilateral field, there are mainly four triangles that are formed. One is FAB, one is FDC, there is EAD, and then EBC. Right? These are the four main triangles that are formed. And the very cool part is, no matter what triangle you look at and look at its orthocenter, you will get that it lies on the radical axis of all three circles.
So if I take like
So the
triangle
reason we're looking
ABC
at
or
orthocenters,
ADC,
yeah.
is gonna work as well?
Okay, so the main thing that is making these work is, okay, let's see. So what is it making it work? When I drop this feet of altitude from F onto AB, that works because now we know that this is going to be 90, and so this point lies on the diameter, circle with diameter EF, because this is 90. And similarly, because this is 90, the perpendicular from A, we are going to get that it lies on the circle with diameter AC. And because this angle is 90, we are going to get that it lies on the circle with diameter BT. So what we want to look at is basically we want to have for each of these three diagrams, we want to have one thing that one that lies on it. That's the idea. So for each of them, so EF, at least so we have three things. We have EF, AC. So one nice way to consider this is in our triangle, at least one of these things from each of these should come as vertices. That's one sanity check. Because if we have F as one of the vertices, then that's a nice thing because whatever it is that we are dropping a perpendicular on, that point, if we just join it to E, we are going to get that it lies on the circle with diameter E. Also, it will be nice if the thing is, it will be nice. Let's say we're considering F as one of the vertices of the triangle. Then we want it to somehow get connected to E. So it doesn't really make much sense to look at a triangle which has F, G, B, let's say. Because if we drop a perpendicular from F to GB, let's say it's somewhere here, it doesn't really give us much of a connection to EF, the circle with diameter EF. That'll be more towards a circle with diameter F. That'll give us something related to that. So, which is why these are the four main triangles that sort of work out. So over here also, I think somebody's question may be lavish and might be wrong. But how does this work out? Again, it's very similar. Did you figure it out?
No, I was listening to you.
Okay, fair enough. So
I
let's
think
again call this point. Yeah, go on.
I think this is the idea of radical center, right? It was discussed in chapter
Yes.
2 or something. Yeah.
Yes, so we have x, y, z. Now we know again observe that x, since fx is perpendicular to ex, we know that x lies on the circular diameter EF. So the power of this point, let's call it h. Okay, I'm a double naming. Let's call this h prime, y prime, z. So power of h prime with respect to the circle with diameter EF is going to be h prime. This is supposed to be, no, what is this supposed to be? F. H prime F into H prime X prime. Now, similarly, since A Y prime C is 90, just by definition, we know that Y prime lies on the circle with diameter AC. So the power of H prime with respect to that circle is H prime A into H prime Y.
Okay, got it, got
And the
it.
last one is this 90. And that's this
Yeah, got it. Z dash
same
H
thing.
dash H dash B.
Yes. So again, H prime has the same power with respect to all the circles. So we know it has to lie on the radical axis of all three circles. So let's write down the very cool facts that we have. So this is called like the complete quadrilateral concept. So yeah, ABCD, we extend all the things possible. We in every pair of points and extend them and consider every intersection. And that's how we get the complete quadrilaterals. So AC, BD, and EF are called the three diagonals, I believe. And the Gauss-Borden-Miller theorem, I'm not sure if I'm pronouncing it right, it states that the midpoints of these three are collinear. And that simply follows because we know that the three circles we just mentioned, they're coaxial. And when we have three coaxial circles, their midpoints, the centers have to be collinear. And the centers of those three are just midpoints of EF, BDEs. And okay, let's write this down. So the first nice result we get is midpoints of EF, BD, AF collinear. The second nice result we get is the four orthocenters of FAB, FCD, EAD, EAD, and EBC are also collinear. And the third fact that we get relating these two lines is that the above two lines are perpendicular to each other. I think this is very cool because it's fairly unexpected. What it's saying is just take any possible quadrilateral that you can, and just look at these four orthocenters, look at these midpoints are going to be collinear and perpendicular. That's very cool. Yes. Amazing. Okay. Shall we move on to the next one? Okay. Number three. Let's copy paste it here. Okay, we have in circle of triangle ABC. And it touches sides BCCAB at DEF. Now we are considering four circles. One is circumcircle of ABC. Then we have circumcircle of AEF, circumcircle of CAD, circle of DB. And we intersect it with the bigger circle. Call the points P. So this one is Q. Okay, this is such a bad diagram because over here my circle is intersecting the other circle at 3 points. Let's try to fix that.
Otherwise, it would be have intersected at one single.
Yeah, maybe something like this. Not bad. Okay. R. And now we want to show PD, QE, RF concur. I really hope it works out in my diagram. Okay. PD, QE, and hang on, we can still make this one. Yeah. It's just a good Oopsies. I don't know what keeps happening with the internet. Sorry about that. Can you hear me all right now, though?
Yes.
Okay. Amazing. Hopefully it won't happen again. Okay. So, what was I saying? Yes, it will be very nice if, since we want to show that they're concurrent, it would be very nice if we can find some pairs of circles for which these are the radical. So, any conjectures for what these circles could be?
We can notice maybe that API is 90, and similarly CRI is also 90, something like that.
Oh, right. So there was, so notice that, okay, amazing. I'm not sure who said this, but all these three circles are actually, they concur at I. Again, these are my beautiful drawing skills. So notice that the circle that passes through C, E, and Q, that's basically just a circle with diameter CI. Because IQC is 90 and IEC is also 90. Similarly, the circle that passes through EIF also passes through I. The circle that passes through BFQ also passes through I. So we know that these three circles concur. Okay, so as we get more information, we should keep updating our figures. A, B, C. Be something like this. Let's say this is I. Okay. D, E, F. E, Q, R.
Why did that happen? Can you repeat it?
Sorry?
Why did that happen? Like, why are they passing through?
Oh, that's simply because the circle, that's because A, E, I, F are concyclic. And that's because A is perpendicular to AE. Sorry, IE is perpendicular to AE and IF is perpendicular to AF.
Oh, okay.
So what are the circles that we could possibly look at to show that we want PD, QE, and RF to be the radical axes? So I didn't really notice this before, but all of these sort of keep coming back to the orthocenter conflict in a way. So recall how in the orthocenter conflict, we show that one way to show that these are concurrent is to just look at this circle and this circle and this circle and look at their radical axes.
We could maybe draw 3 circles with diameter AD, BE, and CF.
Oof, why would that help? So when I say it's sort of like the orthocenter, I mean it in a way that there aren't going to be many 90 degrees actually. In the sense that if we want to, yeah, it's fine. I don't immediately see how that would work. So it's pretty scuffed. But okay, so one nice way to do that would be maybe look at let's say you want to show DP and what DP, QE, RF are collinear. So if we can show concurrent. If we show PD, QE is cyclic, then similarly QE, RF would be cyclic, and similarly RF, PD would be cyclic. And then we can just look at pairs of these and get that, okay, for these two, the radical axis is QE. For these two, the radical axis is RF. And for this one, the first and the third one, the radical axis is PD. So if we can show that these three are cyclic, then we'll be done. Right?
Yeah.
Okay. That seems like a more approachable thing to do. Maybe let's just focus on those things. We have this, this. You want to show that B, D, Q, E is cyclic. Okay, maybe we can just start listing down the angles we know already. We can get something. For example, we know that APE is the same as AFE. Right? AFE are cyclic. AFE is equal to one angle, another angle that AFE is equal to. So again, remember that DEF is the inner circle of ABC. So what angle is AFE equal to?
Can you repeat?
Yeah, so we know DEF is the inner circle. What angle is AFE? We know AF because of this cyclicity. Now, It's actually equal to another angle. AFE is equal to another angle.
AFD.
AFE is equal to which other angle?
AIE.
AIE. Okay, I'm not sure if introducing I is a very good idea. Since we know that, okay, here's a hint. We know that AB
Like
is
FDE?
tangent to FDE,
FDE?
exactly. Exactly. That's simply because of tangent secant theorem. You know that this is tangent and this is the chord, so the angle made by the chord with the tangent is the same as the angle made by the chord in the circle. Maybe drawing this would help. Okay. Interesting. And we also now want to do something with okay, we haven't yet used the fact that QDFB are concyclic. So let's also use that. We know that this angle plus this angle is going to be 180 QBA. And we know that QBA is equal to QPA. So we can basically compute, point being, we can compute angles QDE and angles QPE in terms of just the green and pink angles. So let's call the pink angle, let's say X. So QBA is going to be 180 minus X. Similarly, QPA is going to be 180 minus X. So QPA is 180 minus X. And we know this angle, let's say, so APE is also Y. So compute QPE. What is angle QPE?
X plus Y. Sorry, 180 minus
No,
X plus
it's
Y.
angle. Yes, it's 180 minus X plus Y. That's because it's angle QPA minus angle APE. And we know that QDE is X plus Y. Still done. So Q and similar arguments, we also get uh, Q similar argument. We get that the FR and cyclic and it's really weird. Not sure why it down now. Sorry. Okay. and also FRQE consent done by radical axis.
Could you go back a bit, like from QPE? Okay.
Okay, any questions about any of this?
Yeah, like could you explain it once again, like how it all happened?
Okay, so which part do you want me to explain? The angle case or why we are done once we know that they're cyclic?
Wait, so QPE is like 180 minus x minus y. That part I can.
QPA, and we know that APE is y. So PE will be 180 minus x minus y. Did that make sense? Sorry, I think there's some weird things happening with my internet today. Does that make sense?
Oh,
Why it's
okay,
180
okay.
minus x
Got it,
minus y?
got it. Yeah, got it. Yeah.
Okay. This big angle is 180 minus x, the small angle is y, so this angle is 180 minus x minus y. And we know this is x plus y, so we are done. So for people who know directed angles, this would actually be considered more correct with directed angles because there are some configuration issues. For example, B and D could be on the same side of QF, and then they would both be equal to x, and things like that. So I always recommend using directed angles. But anyways, this
In
was
my
really cool.
diagram,
Yeah.
in my diagram, like I found like Q is on the other side of B. So in that case, like things are like I see like weird here because the cyclic quadrilaterals are different here. So but the solutions are the same.
Yes, the solution is essentially the same. So the reason is sometimes, so this is called a configuration issue, but it all works out the same. If you do it using, so in an actual contest, it's always better to mention directed angles. It's always better to go through all the possible configurations just to be sure, because sometimes marks are cut for config issues. But the directed angles is the way to go. So we might have a small part of a class on it, or you can just read up about it on Evanson's book in Euclidean Geometry in Math Olympiads. So it's basically a way of, I wouldn't want to call it cheating config issues, but yeah, if you do it using, if you let's say do some angles using directed angles, then you don't really have to worry about such configuration issues. Okay. Okay, amazing. There's one last idea I want to discuss before we start today, and that's the idea of a point circle. So, cool, because this is the idea that when you have a point, that also is a circle with radius 0. I think you might have discussed a little bit about this. So before we move on to somebody was saying something? Okay, amazing. So let's do a little bit of easy questions before we move on to a big question about using point circles. So let's say I have a point circle and another circle. Or let's say I have 2-point circles, which is basically just 2 points, but I'm going to consider them as circles. Oh, how does showing that there are circles finish the problem? Just use, since these three are circles, you just use radical axis theorem on these three. So the radical axis of QPDE and PDFR is PD. The radical axis of DPFR, FRQE is FR, and FRQE and QPDE is QE. By radical axis theorem, they have to concur at a point. So we know that PD, EQ, and FR concur. That's what we wanted to show. I hope that made sense. Okay, let's say we have 2-point circles. Then what is going to be the radical axis of 2-point circles?
Like the perpendicular bisector joining the line.
Exactly.
Joining the centers actually. Sorry.
So again, since the radius is 0, if you recall the formula for finding the power of a point with respect to a circle is just, if the point is P, then it's just PO square minus the radius square. But here the radius is 0, so the power of a point with respect to a point circle is just going to be the distance from the point to the center of this point circle squared. So let's say this point is O, and let's say this circle is something, then O squared omega. Then power of any point P with respect to this point circle omega, power of any point P with respect to the point circle omega is just defined to be as PO squared. So as Sharanya said, the radical axis of 2-point circles is just going to be the perpendicular bisector of the line segment joining the 2 points. Now, a
The
very
claim
cool consequence of this, yeah.
The claim you have just now told holds, that's why, because OP is tangent to the circle with 0 radius.
That's one way to think about it. Another way is into the formula that we had. So what was the formula? The power of a point with respect to a circle with center O is just, if we have this point P, then I think Pranav mentioned this formula that it's OP square minus R square, right? Where R is the radius of the circle. Power of the point. Power of P is this. So now we just plug in, a point circle is basically a circle with radius 0. So it's just a point, but you're kind of scamming into considering it as a circle with radius 0. So since the radius is 0, the power of a point with respect to a point circle is just going to be the distance between the 2 points squared. That makes a little bit of sense. And also hopefully you'll see why point circles are useful. So what we have is this. Right. So the perpendicular bisector. So a very cool consequence of this is existence of the circumcenter. So can somebody, so question, show that the 3 perpendicular bisectors, the perpendicular bisectors of the 3 sides in a triangle concur
We can just let A, B, C to be the 3-point circles.
Amazing. So, as you mentioned, we can just consider point circles at ABC. Done. Okay. Something in the chat? Isn't that kind of cheating? Yes, so it does feel very much like cheating, but it's also very useful. So one more thing I want to do before we actually get to the question is if we have a circle and if we have a point on the circle, let's call the circle omega, the center O, this point, let's say A. What is the radical axis of point circle at A and omega?
Perpendicular bisector of EO. Radius EO. Oh wait,
Perpendicular
or
bisector of
maybe
AO,
maybe just the tangent at A.
tangent at A, okay.
It's even
And why is
zero.
that?
The power point is 0.
Why is this the radical axis? Somebody just quickly explain why this would be the radical axis.
If you take any point on the tangent, then the power points are the same.
Amazing. That was all there is. So the power of this point, let's say P, with respect to omega is going to be PA squared, but power of point with respect to A is also going to be PA squared. So we are done. That's just going to be tangent. Okay. Tangent to omega at A. Another case to consider is when we have a point circle outside. What is going to be the radical axis of A and omega now? And this one's not that neat of an answer. Okay, maybe it is, but maybe not at this point. Maybe this can be left as a homework exercise. So we can at least start discussing this other problem I wanted. No, I guess the buffer problems will just be added to the problem set. So there's this one particular problem. This is also from last class that I want to discuss, which is related to point circles. It's very neat, but it's also slightly challenging. So we have, let me see, be a triangle. Yes, so we'll see if we
This
use
was
point
the buffer
circles in
problem
problems.
actually.
Oh, this was the buffer problem. Okay. It's fairly challenging. It's not an easy problem. So we have D is a point such that BD is equal to CD. Okay, so let's take this. PQB points on DCD such that AP is EP and AQ is CQ. So something like this, maybe. This is P, this is Q. Prove that as D varies, the line PQ passes through a fixed point. So have you guys had a chance to try this problem yet? Before, since it was given as a problem in the last session.
Yeah, but I didn't get the answer. Just observations.
Interesting. What are the observations you got?
The circumcenter is the radical center, and
No,
wait,
no, no,
I
no,
wrote
no. You're not. The circumcenter of what is the radical center of
of
what?
ABC.
The circumcenter of ABC is
The radical center of the three, I don't know. Like I took ABC as the centers of like three circles, and don't touch the radius of what, and then you like, oh yeah, wait, 1 second. Just
yeah, no worries.
yeah, DO and PO and QO, these are like the radical axis. Am I right there?
Okay.
So they meet at O. That's why I said like that's the radical center.
Okay.
But according to like my solution, PQ was like moving away. So it's definitely wrong.
Okay, first thing, okay, this seems like a pretty intimidating question. It would be to make some conjecture about what that fixed point is. What could the fixed point be? So this is again, I'm not sure what the best way to motivate it is, just by drawing a lot of diagrams, or just by drawing one diagram and observing things in it. So maybe at this point it's fair to resort to GeoGebra. So we have a triangle and oops. Okay, let me just, I'm not sure what this is. Okay, better. We have it. What? Okay, better. We have a triangle ABC. We have the perpendicular bisectors of all three. And we have a point varying on the perpendicular bisector of BC. And we join it to meet the other perpendicular bisectors. And those are going to be our P and Q. And as D varies, we want to find out what is the fixed point that it's passing through. That point seems to be somewhere around here, right? Somewhere around here, that point seems to be. Any conjectures? Time. Interesting. That's a big hint. Firstly, it seems to be lying on BC. Is there any other way for us to characterize? Also, it seems natural to somehow look circumcircle of ABC because somehow the circumcenter is involved. So let's try to do that as well. So any other conjectures for what G could be? It's some specific point that is not dependent on D at all. This is sort of really hard to see, and I'm not sure how to motivate it because the way I observed it was just by like a accurate diagram drawn in my notebook. So maybe it's just some part of an intuition that comes after solving a lot of problems. But if I just join G to A, then as you can see, GA seems to be tangent to the circumcircle. And that's exciting. So now we know that G is a point that does not depend on D at all. And we want to show that it's collinear with E and F or P and Q in the diagram as in the original question. So now what we can instead do is we can convert this problem into a concurrency problem. Initially it was a problem we needed to show that it passes through the same point. Now we have a proper definition of G, which is tangent at A, cap BC. And what we want to do is we want to show that PQ also passes through it. So now it's a concurrency problem. And that is much more familiar to us because now if we can somehow have AA, if we can somehow show that somehow come up with three circles for which this tangent, this BC, and these PQ are the radical axes. Will be done. And that's where the point circle comes in. So one obvious circle to consider is ABC. And now, since we also want one of the radical axes to be this tangent, we consider the point circle at A to be another circle. So now we have two circles already. One is the circumcircle of ABC, the other is the point circle at A. We just want to figure out another circle. Now, so that takes care of this line. We also want somehow BC to appear. So it will be nice if the third circle passes through BC. So we want another circle that passes through BC, and that will take care of this line, and somehow we also want this to come. So note that we are still yet to use the fact that F is a perpendicular bisector of AC and E lies on the perpendicular bisector of AP. So we have two circles already. One is the point circle at A, the other is this. And now we also know, so we're almost done. So we just need a clever way of defining the third circle passing through B and C, so that this line is the radical axis of point circle at A and the circle through B and C. Since we're out of time, maybe this can be left as a homework exercise. It's definitely not easy, but I feel like I've given away way too many things. There's still a lot of the problem remaining to solve, but I don't want to spoil it at this point. I think it'll be a good idea to think about it for a while. I do hope that whatever I just said made sense about the point circles and the circumcircle and a circle passing through B and C. So it's a slightly clever idea, but I'm sure you'll get it.
Where is this problem from?
Yes, the source of this problem is Lamau 2023 P2. You can find it on here, please. Oh yes, do you want me to repeat the source? LMAO 2023 P2. Okay. So if there are no more questions, I think we'll take a pause here. I think it's good to have a cliffhanger or a suspense sort of a thing. And as usual, you can feel free to reach out on the server as well if you have any doubts, if you're stuck on something, or if you want your solution checked, or anything like that.